So welcome to the next unit of acids and bases, the pH scale. By the end of the unit, you should have a knowledge of how to calculate pH for strong acids, and a change in one pH unit represents a tenfold change in the hydrogen ion concentration, H plus or proton, and you can actually use pH values to distinguish between acidic, neutral, and alkaline solutions. And also discussing the ionic product constant, Kw, and what it is, and how that links to pH. And therefore, by the end of the unit, you should be able to at least solve some problems around strong acids and strong base pH calculations, and be able to use a pH meter and universal indicator. Okay, so the pH scale is a way of expressing the strengths of acids and bases. Instead of using very small numbers, we just use the negative power of 10 of the concentration of the proton or hydroxide ion. Okay, so in that case, pH 1 is 10 times stronger than pH 2, pH 1 is 100 times stronger than pH 3, pH 1 is 1,000 times stronger than pH 4, etc. Okay, and basically the standards we have are that a pH of 7 is neutral, anything under 7 is acidic, anything over 7 is basic. So in terms of calculating pH of strong acids like hydrochloric acid, sulfuric acid, and hydrobromic acid, use the following equation. pH equals the negative log base 10 of the concentration of the proton in solution. Okay, and of course it's going to be in moles per decimeter cubed. And if you work backwards, you can work out the concentration of the protons in solution if you take the anti-log of the negative pH. Or another way of looking at that is the concentration of the proton is 10 to the power of the negative pH. Okay, so those are basically the one equation rearranged that we'll be using. Another important concept is the concept of the ionic product constant of water, or Kw. Okay, so in solution, not even in solution, basically, if you have a cup of water, the water actually itself undergoes a slight ionization. So the water forms an equilibrium, protons and hydroxide ions. And if you apply the equilibrium law, Kw, or in this case Kc, equals the proton concentration times the hydroxide concentration divided by the water concentration. Okay. Now, because the water concentration in that particular case is massive compared to the concentrations of the protons and hydroxides in solution, we don't really care about it. Okay, so the only thing we focus on is the concentration of the proton and the concentration of the hydroxide in solution. Okay, so that means that the constant is combined with Kc to get a new constant, Kw, at 25 degrees. Okay, so it is temperature dependent. Kw equals the concentration of the protons times the concentrations of hydroxides. Okay, at moles squared decimeters to the power of -6. Now, because the constant is based on the equilibrium Kw, obviously this value will change as you change temperature. Okay, so that would mean, of course, that the pH of a solution, as we'll discover, changes with temperature. pH of water changes with temperature. Okay. Also note that this is the key. pKw equals 14. Surprise, surprise. Which is the pH of the proton. Well, the pH plus the pOH. Okay, so basically at neutral, pH 7, the concentration of protons in a glass of water equals the concentration of hydroxide. Okay, so as discussed, this Kw does change with temperature. Okay, so Kw, this association of water, gets larger as temperature increases. That means the concentrations of protons and hydroxides gets greater, and that means that the equilibrium actually moves to the right. So if the concentration of protons increases, then pH decreases. So therefore, using that logic, pH decreases as temperature increases. So as the temperature of water increases, its pH actually gets more acidic. So because the equation moves to the right, as temperature goes up, it is therefore an endothermic process. It requires energy to be pushed into the system in order for it to occur. So let's do some simple calculations with the equations that we have done. Okay, so let's just try and first calculate the pH of a 0.2 molar hydrochloric acid aqueous solution. Okay, so again, pausing the video now and seeing what you can get. Okay, so the concentration is 0.2 mole. That's key. It's a strong acid. We haven't done any weak acid calculations yet. So hydrochloric acid plus basically dissociates into protons and chloride ions. That means the concentration of H plus must be also 0.02 molar because it's complete dissociation. And when I say dissociation, it means that the hydrochloric molecule breaks down into the two corresponding ions 100% completely. Okay, so the pH therefore is negative log base 10 of the proton concentration, which of course is the concentration of the acid itself, and it's going to be 1.7, which makes sense. You'd expect a 0.2 molar solution of hydrochloric acid to be a pH of around about 2. Okay, so final question, calculate the pH of 0.1 molar sodium hydroxide. There's an additional step in here, but I won't give away too much. So pause the video now and let's see what answer you get. Right, so sodium hydroxide, of course, dissociates completely into sodium ions and hydroxide ions. Concentration of hydroxides is 0.1, okay, because of this complete dissociation. So that means that it must be 10 to negative 1 moles per decimeter cubed. Okay, there's two ways you can do this. First one uses kW, the other one just uses pHs. Okay, so kW we now know is the concentration of protons times the concentration of hydroxides, which we know is 1 times 10 to the negative 14. Therefore, we can rearrange the equation to get the concentration of protons, which will be 1 times 10 to the negative 13. Therefore, the pH will be 13. That's one method. The other argument you could say, well, the pOH is 1, pH or PW, the pH of the combination of pH and pOH is 14. So therefore, 1 plus pH must be 14, so pH must be 13. Okay, so there's two ways you can do that. Keep in mind kW for when we do the HL stuff, because that will become more important. But that's pretty much all we're doing for this particular unit. We're going to be moving on further to investigate acids and bases in the next unit.